Okay, and we're live. Okay, well, thanks everyone for coming today. Today we'll be having Paul Daoudi joining us as our guest speaker. Paul holds 2 master's degrees in machine learning and applied mathematics and is currently finishing his PhD in collaboration with Huawei's Noah's Ark Lab. Paul's research aims to move RL beyond the traditional tabula rasa style approach and is focused on integrating prior experience into RL frameworks. Today, he'll be speaking with us on his work in using RL methodologies that are applicable to real-world environments, something here that our teams at InstaDeep are very passionate about. So feel free to ask questions throughout the talk, either raising your hand or through the chat. We'll also have some additional time for questions at the end. So with that, Paul, I'll hand it over to you.
Okay, thank you for the introduction, Donald. Sorry. So yeah, today I'm going to talk about the work that I did during my PhD entitled Reinforcement Learning for Real-World Systems. So it's work that I've done at Huawei under the supervision of Merwan Barlier and Ludovic Dos Santos, and at GIPSA Lab from Grenoble University under the supervision of Christophe Prieur and Bogdan Rogul. So as Donald said, don't hesitate to interrupt me to ask questions. It will make the presentation more interactive. So, as you know, reinforcement learning has provided huge successes in artificial domains, and now we would like to move beyond artificial domains to real-world systems. It can actually provide amazing policies in systems, and it would have huge benefits for real-world systems, and you can apply it in various applications. So we can cite autonomous cars, antennas, the control of server rooms or throttle valves, even in advertising. So it has potential huge benefits for real-world systems. However, it's very complicated to apply it on such systems because of many challenges. First, it's time-consuming usually to gather data from real-world systems. You can think of systems that include heat transfers that are very low, or other kind of industrial systems. So you have to work in a low data regime. And on top of that, you have a poor sample quality at the initialization of the reinforcement learning agent. And it will sample data with poor quality. And again, on top of that, you have safety constraints to respect, because you cannot try anything that you want in a real-world system. So if you take the example of an autonomous car, you cannot break the system in order to learn. So you have to learn without breaking safety constraints. So as a research direction during my PhD, I focused on introducing external knowledge to this framework. And it took, for now, the direction of 3 different projects. That is on offline, policy-guided, and off-dynamics reinforcement learning. So as a prerequisite for this talk, I hope you are familiar with the Markov decision process, with the goal of maximizing the expected cumulative rewards of the MDP. I hope you are also familiar with visitation distributions and with the approximate policy iteration framework, where you first estimate the Q function associated with a policy pi-k, and then you improve pi-k using this estimate. So I hope everything is clear for now, and I'm going to talk about the first project that I did on offline reinforcement learning, which led to a publication at the ICLR workshop in 2022. So in offline reinforcement learning, it's actually a very hot topic in reinforcement learning because it alleviates many of the discussed challenges. In this setting, you have to work with a fixed dataset that has been gathered with an unknown behavioral policy by beta, and no additional interactions are allowed with the environment. So you need to learn only with this fixed dataset, and then you will deploy the agent. So since you don't interact with with the environment, you alleviate many of the discussed challenges. The problem in this setting is that traditional online off-dynamics reinforcement learning agents usually don't work. And most of them are based on the approximate policy evaluation step, which estimates the Q function associated with policy pi_k. And you can understand why it won't work if you look into the Bellman equation that uses the estimates of the state action pair S prime A prime, where S prime belongs to the dataset, but A prime is sampled from policy pi_k. Which means that if this state action pair is not described by the dataset, our estimate QK will extrapolate its value for the state action pairs. And usually extrapolation doesn't really well for neural networks. And this will lead to a Q-value overestimation problem. This Q-value overestimation problem is actually problematic even on online reinforcement learning. But on offline reinforcement learning, it will simply not work at all. So the solutions provided by the community are simply to stay close to the dataset coverage. You can do so with a policy penalization or with a Q value penalization. And then I've focused on the conservative Q-learning algorithm, which is still a state-of-the-art agent in the offline reinforcement learning setting that penalizes the Q values associated with out-of-distribution actions. It basically provides a 0-1 regularization on unseen actions, and it does so by adding a penalization to the Bellman update, which penalizes the Q values of all the states belonging to the dataset and all the actions that are possible in the action space, because U is here a uniform distribution on the action space. Since you don't want to penalize all the Q values, you also add a maximization term of all the action state pairs that belong to the dataset. And this leads to an expected lower bound on the true Q values. So the objective is here well formalized. It's a little bit harsh, but it works very well in practice. So here I've proposed a visualization to understand how it works. On the left, you have the density of the behavioral policy pi beta, and you have the dataset actions that have been gathered with this behavioral policy. And on the right, sorry, you have the penalization associated to DQL that for every that will penalize every actions except the one belonging to the dataset. It's working well, but it has mitigating performances in low data regime. So when you don't have many data state action pairs in the dataset. So that's why we proposed a regularization based on the density of the dataset. So we introduce a smoothing based on the learned density of the dataset, because we want to refine the regularization to take neighborhoods of actions into account. So if an action is not present in the dataset, but is close to, with respect to some kind of distance, to one action belonging to the dataset, then you don't want to penalize its associated Q value too much. And this refined regularization leads to a tighter lower bound on the true Q values. So we've tried it on different offline reinforcement learning settings, and especially in the low data regime setting, where we usually have slightly better performances than conservative Q-learning, but we still have a high variance, and we are not that much statistically significant. That's why we believe that when you have access to few data, offline reinforcement learning may not be enough. We need for additional expertise. And that's why we considered the following two projects that I will talk about, which is online reinforcement learning with local guides and working with simulated environments. So the second project that we did is on policy-guided reinforcement learning, which led to a publication at AMAS last year. And again, the long-term objective is to be able to control real-world systems. And real-world systems are usually often heavily studied by experts. And experts can provide usually a guide for the reinforcement learning agents For example, with optimal control, if parts of the dynamics of the environment are estimated. You can also assume access to a subtask solver, not the whole task, because it may be very complicated, but some subtasks may be simple, so you can imagine having access to scripted procedures. So this kind of expertise may not be global, it can be local, which means relevant only in a subspace of the state space. And we considered in this project two kinds of local guides. We have attractive guides that may be subtask solvers, or just guides that will help the exploration of the agent because it will guide it toward relevant parts of the environment. But you can also have access to repulsive guides. So if, for example, in environments that have safety constraints, you can imagine having access to an emergency procedure. If you take the example of the control of the server room, if the reinforcement learning agent tries too many bad actions and the server room begins to be too hot, you can always have access to an emergency procedure that will cool the room down. It's not optimal at all, but at least it will make the agent remain in a safe space of the environment. So in this project, we focused on integrating this knowledge to the reinforcement learning agent. So this is how we formalize it. So it's similar to reinforcement learning with guides. So that means that on top of the state on the reward, the agent have access to a guide policy by G. But on top of that, it has access to a confidence function lambda that says how confident the guide is on state S. We assume it is an external information that we have access. It's not learned. And we assume we have access to it because when an expert provides a guide, it usually has an idea on where it is relevant. And Lambda doesn't have to be perfect, but we just want, we think it's an information that we already know. So with this, we expect to have a good initialization of the reinforcement learning agent. If it's an emergency procedure, we want the agent to respect the safety constraints. And we want also the agent to overcome the guide suboptimality, if it's suboptimal. So this problem has been studied in the case of global guides. And when you have access to a global guide, usually you have these baselines. So you have the underlying reinforcement learning agent, which we used soft actor critic. So it doesn't use any guidance. So it's a lower bound to beat. We have a reward guided agent that uses reward shaping with a behavioral cooling loss. This agent has a bad initialization and it's very hard to tune it. It's actually very, very hard to tune it. But eventually it's able to overcome the guide suboptimality because you can reduce this behavioral cooling loss over time. You have also the strict action guided that simply switches between the controllers. So when you have access to the guide, you use it. And when you don't, you use the traditional reinforcement learning policy. This agent has a good initialization because when the guide is available, it uses it. It doesn't have any hyperparameter tuning, but it won't be able to overcome the guide. And finally, you have policy improvement guided, which is a state-of-the-art agent in the case of reinforcement learning with guides that penalizes the approximate policy iteration step with a behavioral coding loss. So it's similar to the reward guided agent, but also in the API step that is much easier to control. So the hyperparameter tuning is still hard, but much simpler than for the reward guided agent. It still possesses a relatively bad initialization because it only relies on its estimates to learn. And even if the estimates are learned with a penalization, at the beginning of learning, since you don't have many data, the estimates will not be good. So it has a bad initialization, but it will be able to overcome the guide because, again, you can decrease the strength of the behavioral coding loss over time. This is why we proposed a new agent, which is called Perturbed Action Guided. And our agent is quite simple. If we have access to the guide, we start close to it, and we progressively improve on the guide. And if we don't have access to the guide, then we use the reinforcement learning policy. So this is how we formalize the agent with PyK PAG. So again, if we have access to the guide, we use it. And we also add a perturbation around the actions provided by the guide. We also add a scheduler beta, which we set to 0 at the beginning of learning. And once you gather enough data, you progressively set beta to 1 because Xi will be relevant and will be able to correct the guide if it provides bad actions. We also can make it bounded, which means that if we want to make sure that we want to stay close to the guide, in case the guide is an emergency procedure, where we don't want to go far from this procedure because it will not be safe, we can, thanks to the boundedness property of Xi. And what's good about reinforcement learning is that you build a global Q function that you can use to improve both the reinforcement learning policy by theta and the perturbations that we've introduced Xi. So this is our agent. And we've tested all the baselines and our agent on different environments in the paper. We've considered access to attractive guides and repulsive guides. So for example, in the case of point fall, the agent has to go to the blue square, but cannot do so because of a void. It has first to push the green square on top and then go to the blue square. So we imagine having access to a guide that pushes the green square on top, but does so in a suboptimal way. In the case of repulsive guides, we always have access to an emergency procedure that will make the agent safe at all times. So for example, in the cart pole agent, where the goal is to put the cart up, the pole up, sorry, we've added hard safety constraints where the agent cannot go too far on the left or on the right. So the emergency procedure is simply when you are too far right or too far left, you go back in the middle. So in the case of attractive policies, we found to have a better initialization of all guided agents with the attractive guide, which is good. We have SAG that has a good initialization, which is a switch agent, but it's not optimal because it uses a suboptimal guide. We have PIG that is near optimal and is actually quite good in all environments, but I didn't show it here, but it's very hard to tune. And we have our agent PAG, which seems to be the most efficient at leveraging the local guide. In the case of repulsive policies, the results are slightly different because we have soft actor critique and PIG, which violates the constraints. Since the constraint is made only with regularization, at the beginning of learning, again, the estimates will be bad even with the regularization. So that's why it doesn't work well. And with SAG and PAG, we have no safety violations. And with PAG is less conservative because it's able to outperform the guide. So that's why we observe a better performance. So in this project, we've provided a simple way to incorporate any available guide in any API-based reinforcement learning agent. And we are able to leverage attractive and repulsive policies with an easy hyperparameter tuning. However, we still need to interact with the world, and we've wondered what other kind of information can we leverage. And that's why we've proposed a paper at ISHCAI this year on off-dynamics reinforcement learning. So here we assumed we don't have access to any guide, but we have access to a source environment that is often a simulator. And this simulator can be built with physics or with deep learning models. The advantage here is that you can sample at will without any safety hazards in the simulator. And it's often much faster than sampling in the real world because you can parallelize the simulator and you can basically do whatever you want with it. However, all simulators will be imperfect because they rely on numerical approximation. In the case of deep learning simulators, you may have extrapolation issues, which lead to small errors at every time step. And this kind of compounding errors will be very hard to tackle. Because if you learn simply a policy in the simulator, it will likely not work in the real world. So this problem is formalized as off-dynamics reinforcement learning, where you have access to a source environment that closely resembles the target one, but is not exactly the same. So the reinforcement learning agent learns a policy on the source MDP, and then deploys this policy on the target environment. It's able to collect a small amount of data in this target environment, and then this small amount of data will be used by the reinforcement learning agent to bias the learning in the source environment to learn a new policy that will be better transferred to the target. It may be an iterative process, and in here we wondered how to leverage the few target data. So the few shot of dynamics setting is as follows. You have access to a source MDP and a target MDP that only differs by their transition probabilities. And you have unlimited samples from the source MDP and a few samples from the target MDP. There are currently three different directions to tackle this. The first one is being robust to the source, so being robust to the transition probabilities of the source. The second one is to improve the source MDP with the target data, and it has been heavily studied. And the last one is to bias the objective in the source with the target data. Note that sorry. I see there are questions. Can the rewards be different between source and target? No, in this work, we consider the rewards are the same. We've only focused on a difference between the dynamics. But I assume in some settings, the rewards could be different. That would require another algorithms. So yeah, there are three different approaches, and I want to stress that the last two approaches are orthogonal to each other, because once you improve the source with the target data, you still need to learn a new policy on the updated source, and it's better to bias the objective to have a better transfer to the target environment. So in this project, we focused on the last direction, which is to bias the objective in the source with the target data. So here are the baselines that we considered. We have, again, offline reinforcement learning that serves as a lower bound to beat, because it only uses the target data, and you have only access to few target data, and the other agents use both the target data and the simulator. So again, it's only supposed to be a lower bound to beat. You have online reinforcement learning that is trained on the source environment, which is again a lower bound to beat. You have robust reinforcement learning that is trained with noisy actions. And we've selected A and E, which is actually an old technique, but that outperforms recent robust approaches when the simulator is a black box. You simply inject noise in the actions when you learn in the simulator. You also have the state-of-the-art of dynamics algorithm, which is dark, and that uses a classifier to distinguish between simulated transitions and simulations from the real world. And finally, you have online reinforcement learning online reinforcement learning that is trained on the real world. And this is actually an upper bound to reach. So before proposing our agent, we've analyzed the difference between the objective in the source environment and the objective in the target environment. And you can see that both are linked thanks to the following upper bound. So the objective in the target environment, which is the one that we want to optimize, is higher than the objective in the simulator minus a term that is composed by a distance between the state visitation distributions, and another term that is very complicated to compute because you don't have access to the transition probabilities. Since the term is in red is complicated to compute, we've proposed a simpler lower bound on the objective that uses a distance between transition visitation distributions. And this distance is actually relatively easy to compute thanks to imitation learning techniques. So our agent is, again, quite simple. We maximize the rewards of the source environment while having a small distance between the transition visitation distributions, thanks to the maximization of the advantage related to an imitation learning reward. So as a base algorithm, we used PPO, and as an imitation learning algorithm, we use Gale. But again, we can use any kind of imitation learning algorithm. And in the paper, we show that Gale is actually working very well, but you can use other algorithms. So we've tested the different baselines and our agent on different environments with dynamic discrepancies. So it's always simulated to simulated, but we changed a property on the second simulated environment. So for example, we changed the gravity, the mass, or the friction, and we've also changed, for example, we can break a joint in the cheetah or ant robot, Mijoko robot. And most of the times, our algorithm is outperforming other baselines. And for the baselines, we can see that dark can work well on some dynamics discrepancies, such as the broken environments, but may struggle on others, such as gravity. And that being robust usually helps. It actually provided sometimes the best results for heavy or friction changes, but it's very difficult to tune, and it doesn't work all the time. For example, with gravity, it didn't work that well. So as a conclusion, I would say that offline is often not ready when you have access to only a few data, because you have a high variance, and it may be difficult to tune. And I want to stress that if you have prior knowledge of the environment, then you should use it, even if it's narrow knowledge. For example, in the case of local guides, I recommend to use it. And again, of course, if you have access to a simulator, you should use it. And in the future, I am working on leveraging related tasks that may provide an information to the reinforcement learning agent. But you can leverage any kind of external information. So you can, for example, you can leverage videos from the internet of a task. And I think the possibilities are, I would say, limitless, because the information can take many forms. So yeah, I think this is an exciting direction to follow. Thank you for your attention. And if you have any questions, I would be happy to answer them.
So I think we have a first question in the chat from Tristan. How do you think this would compare, for example, interspersing online RL on source with supervised learning on the target environment, and specifically for the last method?
Can you provide more information on this question? What do you mean by interspacing online reinforcement learning with supervised learning on target?
Yeah, so hi. So maybe I'm understanding it wrong, but like let's imagine I had a limited data set of transitions taken from the target environment. Then obviously what I could do is I could just learn, like, completely independently of any interaction with the source environment, to just imitate those transitions in a supervised way. Right.
Okay. Well, of course, but then you would only reproduce the trajectories that you sampled on the target environment in the simulator, and you would want to improve this to improve the rewards over these trajectories. So I would say we kind of compared with this method with offline reinforcement learning, which is trying to make a better policy than the behavioral policy that was used to sample from the target environment. It's true that we didn't really compare to the purely imitation learning algorithm, but well, I would say it's there is no point of only wanting to imitate the trajectories in the target environment, because you want to find a better policy.
Any other questions, guys?
Is the behavioral policy an expert policy? Okay, this is a very good question, and maybe I wasn't clear enough in the presentation. I assume you are talking about the of Dynamics project.
Yes, exactly.
Well, actually, it's not. We assume so it's the policy that you use to sample from the target environment. We assumed it was the policy that was learned initially from the source without any data. So it's simply the online reinforcement learning that was trained on the source, and it provided medium quality trajectories. And then using this kind of medium quality trajectories, you put them back, you bias the learning in the source simulator to learn a better policy. So yeah, it's an iterative process, and we didn't use any additional expertise.
Any other questions, guys? Okay. If that's everything, I can stop the recording.